Welcome everyone to this video. So today we are going to do a small derivation on the idea of uniformly charged hemispheres. So mainly we want to see that how to think about finding the element which produces an electric field in a hemisphere. So a hemisphere is a body like this, and this is our point of concern, this center of the hemisphere. We'll say the radius of the sphere is some r, and the charge density is purely uh, associated or purely spread on the surface of the sphere. So you can say this is something like a shell, or even if it's a solid conductor, or charges spread like this. And by that, we have some interesting uh, discussion point. Uh, if it were a conductor, would the charge spread out uniformly like that? So, in a conductor, the charges tend to bunch up at the points which have very sharp edges, and which are the surface, which is the perimeter of this hemisphere. So, we want the hemisphere to have that uniform charge density. That means that this hemisphere has to be a non-conducting one. So let us move on to the next step. After having formulated what is given in the question, that is, we know the charge density, we know the radius of the sphere, and we know uh, the laws which we need to apply. We need to apply the Coulomb's law. Um, so if I were to take a ring-like element like this, we can find the field due to this ring at the uh, center point. So many a times a inverse question also comes. What is asked from us is that you have a charge q placed at the center of this hemisphere, and then it is asked what is the force exerted by that charge on this whole hemisphere. In that case, our mind thinks in that direction, that the force exerted by a charge on a hemisphere is in multi-direction. If that charge is exerting force at this point, it would be radially outwards. In fact, at all points, it would be radially outward. So, how can we imagine all those infinite directions, let alone the magnitude of the force? Even if we were to say that the magnitude of the force is a constant only, because all the points are at our distance, how would we think about the direction of the forces? It would make a solid angle. How would we club up all those force vectors? So that is the main critical point. So we simplify our case. We say, if we have taken an element like that, the force exerted by that element on a charge placed at the center of the hemisphere would be same as the force exerted by the charge on the circular element. So instead, we are talking about what is the electric field of the hemisphere because that is easier to evaluate. So let's see, if there's a hemisphere like this, if there is a hemisphere which is of radius r, and this element is making an angle theta like this. So as it is making an angle theta at the center of the sphere, uh, we will say what is the radius of the circular arc. So the radius of the circular arc would be r sine theta. So that means that this arc has a perimeter which is 2 pi r sine theta. So this is what this circular element is, how long it is. What about the width of the element? The width of this element is r d theta. So if we shift our radius vector by this d theta angle, we'll be able to trace the width of the element. So we multiply this width r d theta with uh, the perimeter of the circular element. We then say this is the area of our circular arc. Now we multiply this with the charge density, and we'll say if this charge density is producing a field, then that we can evaluate. So this is small charge Now we want to write what is the field due to this charge element. This was my step 1. Field is simply k dq cos theta upon r square. So if I were to integrate this, okay. So why have we taken this cos component? We have taken this cos component because the force due to this whole element would be uh, in this direction. If I were to take the force due to a charge at this whole ring, so that force would be going radially outwards or radially inwards if I were to imagine a single charge. Uh, so we have to take that element basically. We have to say that okay, if this dq charge was somewhere spread out like that, then what field it is producing basically. So it is producing this much field k dq by r square, right? So we take a cos component of that. We say this angle is some theta. We take a cos component, the sine components get cancelled out, and only the cos components remain. So this becomes k sigma 2 pi sine 2 theta d theta divided. And we integrate this from 0 to pi by 2. So how many people know the integration of sine 2 theta? I'm sure people would recall it just like they did in their classes when they first learned it. So integration of sine to theta is minus cos to theta. Since this is a cos function, and this is 0 to pi by 2. So what is incredible is that how this trigonometry comes in part in comes it into play in electrostats. After solving all of this, we get the result that sigma upon uh, some k into pi is also there, into minus 1 divided by 2 into there is a negative sign here as well. We get sigma upon 4 epsilon. So that's it for today's video. Thank you.